Hello, everyone, and welcome back. My name is Mr. Kovault, and in this video, I'm going to be talking about cell potential under non-standard conditions and introduce you to the Nernst equation. So let's get into this. So we have an equation, right? So we've been talking about cell potentials under standard conditions. That would be, for example, when we're reacting zinc solid with copper 2 ions in aqueous solution under 1 molar concentration, and then that gives rise to zinc 2 ions, again aqueous under 1 molar conditions, and it gives rise to solid copper. So this would be standard conditions, and we know that the cell potential, the standard cell potential, is 1.10 volts. But what if the copper solution, the copper 2 solution, was greater than 1 molar, and that the zinc solution, the zinc copper solution, was less than 1 molar? So if this was greater than a 1 molar concentration, and this is less than 1 molar, what would the what would the cell potential be under those conditions? These would be non-standard conditions. And by Le Chatelier's principle, we could figure out whether or not the non-standard cell potential would be either less than or greater than the standard cell potential. Because remember, if we have a greater concentration of Cu2 plus, the copper 2 ion, remember the copper 2 ion here is a reactant. So if we're increasing the reactant, the amount of reactant, then Le Chatelier's principle says that it's going to move towards the product. So the forward reaction is going to be much more active. So it's going to have a greater tendency of moving towards the forward reaction or moving towards the products. And so you also get the same result if you lower the concentrations of your zinc 2 plus ions, right? So if you decrease this, then according to Le Chatelier's principle, you want to increase it back up. And the way to do that is to shift towards the products again. So having a greater amount of your copper 2 ion concentration and a smaller amount of your zinc 2 plus concentration, then that's going to make the tendency of the forward reaction to be greater. Excuse me. And so we could predict, excuse me, that the non-standard cell potential is going to be greater than 1.10 volts because there's a greater tendency to go forward under these non-standard conditions. So we can actually derive an exact relationship between these two things. So we can get an equation between the standard cell potential and the non-standard cell potential, and that is called the Nernst equation. So how do we get the Nernst equation? So let's look here. So we know that from a previous video that the non-standard free energy change is equal to the standard free energy change plus RT ln of Q, where R is the ideal gas law constant with joules per mole Kelvin. So that's going to be your 8.314 joules per mole Kelvin multiplied by the temperature in Kelvin, and then the natural log of the reaction quotient. We also saw in my previous video that the standard free energy change is equal to the negative of the number of moles of electrons that are transferred during the redox reaction, multiplied by Faraday's constant, and multiplied by the standard cell potential. So if we take this and substitute it in for both of these, we get negative NF E cell is equal to negative NF E cell standard plus RT ln of Q. And so if we divide both sides by negative NF, right? So here we both divide both sides by negative NF. The negative NF is going to be canceled out here and here. So we get the cell potential, the non-standard cell potential is equal to the standard cell potential minus RT over NF times the natural log of Q. So that is our equation here. But now we can plug in certain things. We know that R and F are constants, right? So we can plug in the numbers for those like we did before. And we can set the temperature at 25 degrees Celsius. So under that condition, we can plug that in. And we also have the relationship between the natural log and the log base 10. And so we can put all of that into this equation. And so what happens is that RT over NF times the natural log of Q becomes 0.0592 volts over N times the log base 10 of Q. So now we can take this and substitute this in for this in our equation. And so that's what we do here. So then our final equation here is the Nernst equation. This is the non-standard cell potential is equal to the standard cell potential minus 0.0592 volts over N times the log of Q. So this is our Nernst equation. So let me highlight this. So let's put a box around this here. This is our Nernst equation. So this is the Nernst equation. So a couple of things that this tells us already. So under standard conditions, this is where Q equals 1. Since the log of 1 is 0, this means that the E cell under non-standard conditions will end up being equal to the cell cell potential under standard conditions. And so we could see this from the equation here. So if Q is 1, then the log of Q is 0, and we're multiplying 0 times this. So this whole thing becomes 0, and then so the standard cell potential ends up being equal to, the non-standard cell potential ends up equaling the standard cell potential. So these are now equal to each other. When Q is less than 1, right? So if Q is less than 1, we can see here that the non-standard cell potential is going to be greater than the standard cell potential. And so when Q is less than 1, that means you have greater reactance compared to the products. So again, according to Le Chatelier's principle, if you have greater reactance compared to the products, that's going to shift towards the products. The forward reaction is going to have a greater tendency, and so you would expect a greater cell potential under those non-standard conditions compared to standard conditions, right? So that makes sense. When Q is greater than 1, right? So again, here Q is greater than 1, products are greater than reactants. So that means that the reverse reaction is going to have a greater tendency, and the forward reaction is going to have less of a tendency. So we would expect that the cell potential under those non-standard conditions to be less than the standard conditions. And so that's what we have here. So under this condition here, then the cell potential under the non-standard conditions would be less than that under standard conditions. And then finally, we could see here that when Q is equal to K, meaning that we're at equilibrium, then neither reaction, forward or reverse, has a tendency to occur. And so under that condition, then the standard cell potential is going to be equal to 0. And this is why, of course, batteries don't last forever. So batteries run on chemical reactions. As the chemical reactions go, more products are formed, less reactants are there. So as the reactants decrease and products increase, you're going to reach an equilibrium. And once you reach equilibrium, there's really no tendency for the reactions to go either way. And so your cell potential ends up going to 0. So that's just the way it is. So I hope this was helpful. If this video was helpful, if you enjoyed this video, if you like this video, if you learned from this video, then by all means, please share this video with your friends. Hit that like button, like this video. That like button is right over here. Also, if you subscribe to my channel, right, make sure you do that so that way you can be notified by other videos I put up. And make sure you hit that like button up there so that way you can be notified by my videos that I put out. Also, make sure when you hit that subscribe button, hit the all button after that so that way you can see all my videos or be notified by all my videos. And finally, put a comment down in the comment section below. Let me know what you think. Ask me questions. I'd love to hear from you. Thanks for joining me. Have a great day.